You're live.
We are live. So while everybody's getting lit on here, let me get the slideshow up and running here. All right. I want to thank everybody for attending today, and happy holidays. All right, today we're going to be talking about the Philly Scoreboard expansion project with our colleagues Paul and Mary from Ewing Cole. Pretty excited to go through this one. If anyone's been to the stadium, then you've seen what we're going to be talking about. If this is your first time on the call, this will be the first time you're seeing this. I want to just introduce the board members. If you joined us before, then you've seen this. But I want to thank all of our board members, Michael, Colin, Greg, Alex, Nathan, and Justin for everything they do. Obviously, we're a volunteer board, and it can be a lot of work to get these things organized and scheduled in addition to our regular work. So I want to thank everybody for that. Nikki, you did great last year, and we're happy to have you here as the past chair. So, keep on keeping on. Definitely expect to see you at meetings in future. Wanted to also just remind everybody, SEI Philly golf outing. Obviously, thanks to our sponsors last year, all listed here. Save that date for 5/9. It'll be at Kemberton Golf Club again. Looking forward to having everyone there and having some new people there. That would be fantastic. So everyone does know this meeting is being recorded, and that is so we can then put it up online for future people to review and so forth. We have disabled your microphone and your camera. And if you would like to contribute to the discussion, you can use the Q&A Teams messaging on this, not the chat. So definitely drop your questions into the Q&A. And this will make it easier for us to get responses to your questions. And feel free to drop them in at any time during the presentation. Our intent is to field all those at the end, but it doesn't matter when you put it in. And obviously, with that in mind, give a little bit of reference when you ask the question if we need to from the presentation, just so we can go back to the slide if we need to. Our website listed here, sei-philly.org. Email, phillysei@gmail. The QR code here that'll take you to our email as well. And we do have a LinkedIn area for the chapter. You can see it there. Please join us on LinkedIn. Always looking to have people join us there. Some upcoming events. So obviously today we're doing the Philly Scoreboard expansion. We are looking to put together a virtual in January. We'll have that sort of wrapped up here very shortly. We're also looking to potentially do a winter social. Might be January, could be February. We're still trying to work through that. And also venue for that one. We have a couple ideas in terms of maybe Top Golf or just going to a local watering hole to all hang out and get social. We do have our joint meeting with Delaware Valley Geo Institute. That's going to be at the Valley Forge Casino on the 18th of February. And we'll be talking about dams. Those are one of the I would call one of the few structures that involve pretty much every bit of civil engineering that you could possibly think of and structural engineering, mostly for the outworks and the structure and so forth. Very interesting projects with any sort of dams, whether they're coffer dams or regular long-term dams. I think that'll be a very interesting one. I'd like to see a bunch of people from SEI out at that meeting as well. And that will certainly be in person. And then also in February, we are looking to put together a structural engineering panel for students at Swarthmore College. Certainly would very much enjoy any engineers that are on the call now. If you are a Swarthmore grad, all the more reason to maybe volunteer and give us a hand filling that panel. Um, it'll be held at the college, and we'll have more details as we get that one nailed down. So certainly looking forward to having some attendance there. So for today's speakers, the Paul is the director of structural engineering at Ewing Cole, Drexel grad, yes. He's been doing this quite a long time, and he's got a bunch of experience in terms of structural engineering in general. It's so great to have you here, Paul, and present on this interesting project that we have. And Mary is also structural engineer at Ewing Cole. She has also quite a bit of experience doing structural engineering. And we are excited to have you here as well, Mary. I think it'll be sort of a tag team here for the presentation. What we will do for the PDH is we will have a QR code at the end that you can snap a picture with your phone, so you can claim that QR code. But with that being said, we are going to switch over to the presentation at hand. Thanks again.
Great, Keith. Thanks for the introduction and welcome everybody. Thank you to the SEI board for inviting Mary and myself to do this presentation for you today. Hopefully, everybody will enjoy a little bit of this behind-the-scenes tour of what the Scoreboard structure is and get to learn a little bit about how we were able to pull it off. I'm basically going to tee this one up for Mary, give you a little bit of a brief introduction, and then Mary's going to really walk you through, as the lead structural engineer on the project, through how we were able to work with the ownership of the Phillies and our interior architects to just come up with a display board that would work for them and what they were looking for and how to really make it all come together. So to start with, you could see basically what the park started as and where we ended up, and hopefully you'll have a better understanding of just what went behind the scenes and then the drawings and then the calculations to make this all come about. We intend to cover a whole bunch of topics ranging from just a brief overview of the park's evolution from its original design and construction in the early 2000s, the Scoreboard evolution as the park, kind of evolved through the different phases of the park's age as it's grown from 2004 to present day. And then, get a little bit more in depth with what is the physical Scoreboard structure, the concept of how we were able to look at various opportunities for Scoreboard displays, and then go through the design and construction. As I mentioned, Citizens Bank Park opened in 2004. It was actually designed by Ewing Cole, and the first board that was ever displayed was actually a combined board of two different displays. The lower display was a Phillips product, not that necessarily makes a lot of importance to what we're trying to do to make the board bigger, but there was two different display manufacturers for the original board, and you can see some of the statistics here, the lower board being around 43 feet by 74 feet, and the upper board being 43 feet by 74 feet, basically topping out at around 134 feet above the concourse level, which is down here at the seating. There was also some static signage that was more over the area of the Scoreboard and lighting displays or lighting arrays for the field lighting. The original Scoreboard technology was in its infancy, but it was incandescent bulb technology. A little bit of behind the scenes of what is the Scoreboard area and what makes up that whole structure out there. And it's basically what we call it the Scoreboard building. And basically that Scoreboard building is located and supported off of the box columns that are part of the lighting arrays and the support of the video board. And the video board, again, sits proud of the structure for the display and lighting arrays to provide access for catwalks and various service to the back of the board for its operation. Below the video board building is some restaurant, there's the seating tiers, and then going further below grade, you've got, of course, some service utility tunnel work and other behind the scenes stuff associated with ballpark operations. So, and then Mary will talk a lot about the substructure and more of the structure of the display support, because it was all kind of critical to be evaluated to see what we were actually going to be able to accommodate with the existing structure for the new display. Quickly looking at what is the display structure. This is an early photograph of it under construction back in the early 2000s, and you can see that it's primarily 4 large box columns that are there to support both the display board and the field lighting array. The 2 box columns that support the display board top out basically at about 150 feet above the concourse level, whereas then the sports lighting array tower goes up to another 50 feet higher to around 200 feet above the concourse for the sports lighting arrays. As I mentioned, the display itself for the video board cantilevers off of this structure towards the field around 4 feet, and that's basically to provide room for catwalks and service access to the display modules from behind. There's also additional framing, beams, columns, and trusses that support the various seating tiers and the elevated floor over the restaurant area. A little bit about foundations. The foundations are a very deep structure. They're 120-ton steel, roughly 12-inch, 12 3/4 inch diameter pipe piles. And each of the box columns with the different loading and the wind loading on it has the pile support with pile caps, and the pile groups range from 28 to 40 piles below each box column. In 2011, around 7 or 8 years after the park was opened, the Phillies wanted to go and entertain an upgrade to the display. So in 2011, they rolled out a high-def display, which basically took the 2 displays that were original to the ballpark in 2004 and combined it into one large display that measured around 76 feet by 98 feet, had the Phillies logo on top. And at the time, it was one of Major League Baseball's largest displays. The elevation of the display didn't really change much from what it was originally. I think the original one was at 134 feet. This new display came in at 134 feet. And roughly, it was of the same size and orientation, maintaining the static signage to the center field side of the lighting tower. It was just basically combining the 2 displays into one larger display. There were some modifications that were made at the time, and I think Mary talks a little bit about how we made all that kind of come together with the support of the display structure and the catwalk access. But significant to the technology was that it was more of an LED and high-def format versus the incandescent bulb of the original ballpark. So before I turn it over to Mary, just to kind of finish my tee up for her design, we're going to fast forward, or I guess rewind back to the 2021 spring timeframe when we were approached by the Phillies to start to entertain options of, hey, what could we build? What is the opportunities here that we could have for this display? How big could we make it? And so that was our basic introduction, is to start looking at the structure, look at other major league ballparks. What are the other parks doing for their boards? Where are they located? What are their sizes? And then try to start doing some test fits for everything there. So with that said, I guess it's time to turn it over to Mary, and she can go into like picking it up from those early concept sketches to the actual design.
Thank you, Paul. So when the Phillies first engaged us in the middle of 2022 to look at what could be possible, they looked at a wide range of scoreboard sizes and configurations relative to the structure. They also looked at some different locations throughout the ballpark, but they quickly ruled out different locations and determined they wanted to stick with the existing scoreboard location in left field. You can see some of the board sizes that were considered got quite large, such as that 116 by 206 at the bottom right corner of your screen. That overhung the existing structure substantially toward the center field side. So a number of these configurations would have required adding significant additional structure. That large option would have required adding another column out at the right-hand side to support it. Some of the options where the board got tall, the wind load got sufficiently high on the columns that we considered adding braces off of the back of the scoreboard. But anything like that would have been too invasive on the main concourse layout. So it was decided that we really wanted to just stick with the 4 box columns that we had. And also because there is a restaurant building below this whole video board, reinforcing of existing foundations was not really going to be an option either. So that sort of became the weak link in this problem. And the Phillies expressed that they really wanted to get the largest board that they could get without needing to do any reinforcing to those existing foundations. So that was sort of our limit. And we ran through a bunch of different concept designs to determine what that limiting board size was. Okay, so I think we went too far there. There we go. So the video board size that we determined was the largest we could accommodate ended up being 152 feet wide by 82 feet high. And you can see that red box drawn on top of the picture shows roughly what the existing board size had been. So you can see the board got significantly wider and about 9 feet taller. And I apologize for the Atlanta Braves player on the scoreboard screen. I'm not responsible for this image. I guess one of our architects must not have been a Phillies fan. I'm not really sure how that wound up in these renderings. So the board size that we ended up with had a weight of 116,300 pounds. In addition to the main display, there is a caption board beneath that is 98 feet wide by 4 feet tall. There's also a Philly sign above the video board, which is replaced in a similar design to what had been there, although it did, of course, need to raise higher because of the video board getting taller, but also the architects felt that the scale of the sign was maybe a little bit too small with the larger board, so the sign did get overall larger, and that sign is 27 feet high at the P, which is, of course, the highest letter. On the back of this video board building, there is a Citizens Bank Park sign. It is the same as the original sign. We just had to relocate it because they wanted it to be, of course, at the top of the building, but also centered on the back of the building. So needed to move with the new geometry. I'll talk a minute about the design schedule. We started these concept studies. I think I had my dates wrong when I said 22 before. We started the concept studies in late 2021. And that's when we ran through all those different board sizes and presented the options to the Phillies. They chose that final size by the end of the year. And in January of 2022, we began working on the design of the chosen board. We issued a GMP set in March of 22 and construction documents in June, and then a permit set in July. And we did follow with various design addendums throughout the remainder of the year. Talk a little bit now about the new structure that was required to support this larger video board. So the first piece is we had to extend the existing columns, and there were 3 different types of extensions that we needed to use. The first one I've labeled as number 1 on the screen. That is the light tower column that previously did not support the video board. It only supported static signage. The video board stopped short of that column. So architecturally, the design of that column had a sloped back to it. Since it was exposed and visible, it had that sloped back to it. That was an architectural decision. But now with the wider video board, we needed the building behind the video board to extend to the same width. So we had to install a plumb column at the back and add some additional bracing members to straighten out that column and form the back of the building. Column extension type 2 that's labeled on the screen was the other light tower column, which had been previously enclosed by the existing building, but it did not extend high enough. We had to extend the wide portion of the column up about 9 feet to frame out the back of the building and the new higher roof. And then column extension type 3 are the 2 box columns that extend up to support the Phillies sign, but do not have light arrays associated with them. So for those, they really just had to raise up again about 9 feet just to raise the roof of the scoreboard building, but then also provide support higher for the new higher Philly sign. The second piece of new structure that we needed to add were these boxes to cantilever off the center field side of the structure to support that overhanging video board. The cantilever length on these is about 12 feet. So we just had to add some new columns out at the corners of the building and some bracing elements. We had to add to and replace some of the existing catwalks. These are the roughly 3-foot wide grading platforms that exist between the back of the video board and the front of the scoreboard columns. These provide access for servicing of the video board. Some of the existing catwalks we were able to reuse, and I'll talk a little bit about that later, but the upper levels did need to be replaced over their entire length. And then, of course, we had to make them wider as well to cover the full width of the video board. The next piece of new structure is the new higher roof. This really just really moves the roof of the building up by about one column panel point, so about 9 feet that the roof raised. So we had to add that new roof framing. Then we needed to add some support for that Phillies signage. The direct support of the sign itself was by the signage manufacturer, but we did have to give them points of attachment on the main structure. And we came up with this design for a triangular shaped truss that gave them the ability to support their sign. Now, the caption board below the main video display previously did not extend as wide as the new design called for, so we did have to add some additional framing there to support the increased width of the caption board. And then now looking at the back of the building, highlighted in red is all of the girts that we needed to add to support the metal panel cladding. And at each end of the structure, there were louvers at every level to support the ventilation required for all of the equipment. Now we'll get into a little bit about how we tackled the structural design. Ewing Cole was the original engineer of record for the ballpark. So with that, we had some advantages in that we had access to some of the original design models that were used. But back in the early 2000s, a lot of the analysis was done in these 2D STAD bents, where you might take a grid line and have all of the framing associated with that grid line and load it up and analyze it and see what happens. So we did have access to some of these existing models in the 2D world that we were able to locate and validate, checking member sizes, checking geometries, checking releases, checking the loads that are applied to the structure. So we were able to find 1 or 2 bents. We didn't have one for each of the 8 grid lines, but we were able to find 1 or 2 that were relatively accurate and then update them to current loading and extrapolate and save as and create models for each of the 8 grid lines. Now, for each of those 8 grid lines, we had an existing condition model that just showed how the structure was loaded originally, and then we had our model of the proposed conditions with the new larger board so that we could compare easily between the existing condition and what we were trying to accomplish with the new design. I think I went too far. Okay. So the wind loading on the structure, we needed to update to IBC 2018 or ASCE 716. We did have some information from the original design regarding a wind tunnel study that was done and some of the BOCA loads that were applied to the structure originally. But with the level of modifications that we were making, we felt we needed to update to the current wind codes. So for the main wind force resisting system, we had a number of loads applied. The first being the video board, which we treated as a solid sign per chapter 29.3, and that's the 66 pounds per square foot that is highlighted in purple. Then we used the open sign provisions of chapter 29.4, and we used that for both the Philly sign and the light array. They had different percentage opening assumed and different heights, of course. So the Philly sign wound up being 38 pounds per square foot over the gross area, and the light array wound up being 45 pounds per square foot. Then we had the exposed structure of the trust tower loads of chapter 29.4, which is highlighted in the blue, and that was 37 pounds per square foot over the gross area. For the building below the scoreboard, we did treat that as a typical traditional building, and we used the directional procedure of ASCE chapter 27. And then for the girts and the cladding attachments, we used chapter 30 of ASCE, component and cladding loads. Not advancing. Sorry, my screen is stuck here on this slide. There we go.
Scroll down.
Yeah. Okay, so once we had the wind loads applied to each of those grid lines, we needed to validate the gravity loads that were applied to the models. So in order to validate that, we created some RAM models. This first RAM model that's on your screen there is the superstructure of that restaurant building below the video board. It's what exists above the main concourse, but below the video board. So we use this RAM structural system model to model all of the floor framing and take those reactions and apply them to our 2D STAD bents. Going too far, I think. Oh, there's my second one. Okay. Then we had a second RAM structural system model that we used to model the main concourse and everything below that. So the main concourse is a concrete framed slab, concrete slab with grade beams. And then below the main concourse, there's this service tunnel that runs around the entire perimeter of the ballpark. And so we had the loads of that service tunnel that also needed to be considered when we were looking at the foundations, just trying to capture all of the loads on the foundations. Next, to determine the loading from the catwalks, we created this 3D STAD model. The primary purpose of this was to design those catwalks and to design the cantilevered framing off the center field side. And then also take the reactions from this new framing and apply them again back to those 2D STAD bents. I'm not sure why these slides, I'm having trouble getting them to advance. I apologize. Yeah, okay, so this is just an image showing how we took those reactions and applied them back to the 2D STAD bents. Okay, so now looking back at that 3D STAD model again, we used that again to design the catwalk framing. The catwalk framing needed to support the weight of the video board, but it also had some strict deflection criteria associated with it. And that deflection criteria was given to us by Daktronics, who is the video board manufacturer. At the time of installation, over the entire length of the catwalk, there could not be more than a half inch of differential elevation along that length for installation of the catwalk. And then once the video board was installed, there was a limit of L/400 for permanent loads on that catwalk and a limit of L/240 for short-term loads. But probably the most limiting piece was that there could not be any inflection points in the deflection diagram. So this is quite a long catwalk, and it needed obviously to be constructed in several pieces. And those splices between the different pieces of catwalk needed to have a moment connection associated with them in order to get a smooth deflected shape, because the video board would not have responded well if there was a kink in the deflected shape. So we used this 3D model to check the existing catwalks, and we determined that levels 1 through 5 of the existing catwalks were adequate, but they did lack that continuity that we needed in order to keep the deflected shape smooth. So we did have to add some additional plates to get a moment splice between the existing catwalk sections to get that smooth deflected shape. Then levels 6 through 9 of the existing catwalks, they were constructed at a different time, designed by a different engineer, and they just did not have the stiffness required by the new video board. So we did replace levels 6 through 9 in their entirety, and then level 10 was added. That was an all-new level that was required because of the added height. And then we did also use this 3D model to design the truss members. So here we have the 12-foot cantilever that overhangs on the center field side of the structure. And then we needed to create a backspan to support that cantilever. And that was done with two different types of trusses. The front truss, which is highlighted in green. We, of course, have the cantilevered framing, but then the supports of that truss are the front faces of those two boxed columns. And then we had backspan framing between the two box columns to support that cantilever. And all of that backspan framing was existing. So we were able to get the sizes and get the connections off of the shop drawings and check the strength of those members and also the strength of the connections. And we determined that the existing framing was adequate. Now at the back was a little bit different because of the column extensions that we had to install back there. So we had the cantilever framing off the center field side, and then we had the new column extensions, which form the supports of that truss, and the backspan framing, those vertical and diagonal members highlighted in orange, they were all new as well. So the back truss was a little bit different. We had a little bit more flexibility with what we were going to do there since it was a lot of new framing. So we were just able to design those members and get forces to design the connections. Now, getting back to those 2D STAAD bents, which really were the heart of our analysis, we used those bents to verify the capacity of the existing members. We used those models to size the new members of the column extensions. And we also used it to verify that we were happy with the column deflection that we were seeing at the top of those columns under full wind loading. And really, these columns are quite stiff, so the deflection at the top of these columns was not really substantial. We felt comfortable with what we were seeing there. We also used these 2D models to pull out forces on the connections so that we could verify that all of the existing bracing and beam to column and column splice connections were adequate. You can see on the screen there, I have one of the column bents, all the red circles symbolize all of the different connections that we looked at for this one particular bent. We relied heavily on the 10% rule of IEBC section 1103.2. It's on your screen there. I'm not going to read the whole thing, but the idea basically is for any connection that did not see more than a 10% increase in demand capacity ratio, we did not need to check it for updated codes and in the entirety for the connection. So we compared our existing models to our new models and determined that 193 connections did not see more than a 10% increase in demand capacity ratio, so we did not need to look any closer at those connections. But there were 246 connections that we needed to do some detailed checks on. So for those, we were fortunate to have access to the existing shop drawings. So we were able to get the information for bolt sizes, weld sizes, gusset plate geometry and thickness and all of that. So we were able to pull that information for each of these connections. And then we used RAM structural system to check those connections. We had an in-house spreadsheet that we created so that we could easily copy and paste forces out of STAAD, put them in this spreadsheet, have that spreadsheet reorganize all of the output and put it in a format the RAM connection needed. So we were able to just easily copy and paste out of STAAD and then copy and paste into RAM connection. At the end of the day, we checked those 200 some connections and we determined that there were two that we needed to reinforce. And these were at areas where the new framing delivered a large lateral force into a connection that previously did not have any force delivered into it. So the failure mechanism in that connection was prying of the bolts in the beam to column connection. So we added some stiffener plates to eliminate that prying action and get some additional capacity out of the bolts. And for the new connection design, a lot of the beam to column and brace connections were pretty standard connections that we just used ram connection to design. We did have to do a few hand calculations for some non-standard connections, and the one you see on your screen there is probably the most notorious. This is at one of the column extensions at that sloped column where the plumb column and the sloped column meet up. We created this bracket with a 1-inch thick horizontal plate that extends out to receive the new column base plate. And then we had 1-inch vertical plates, which align with the existing column flanges, and then a 1/2-inch stiffener plate that frames between those two vertical plates. So a lot of this analysis of the plate thickness and the welds required, that was performed by hand. We did not have any program in-house that we could have easily just plugged this into. Once we got through all of the steel design, we needed to take a look at the foundations and verify that all of our concept level calculations were still valid and that we did not need to reinforce anything with the foundations. So starting from the top down, we looked at the base plates. They were, I believe, 4-inch thick base plates with 12 2-inch diameter anchor bolts anchoring them down. So we used ram connection to check the base plate thickness. We used some hand calculations to justify the concrete breakout of these anchors due to tension and shear. We used the pedestal reinforcing as anchor reinforcing to restrain that breakout. Then we used an in-house spreadsheet that we have for checking the anchor rods for bending, because these columns do not have shear lugs on them, so all of the shear needed to be taken by the anchor rods. And then at the bottom of the anchor rods, there are these large anchor plates. So we did some hand calculations to verify that that plate thickness was adequate to bear this tension load in these anchor rods into the concrete. Next, we took a look at the concrete pedestals that the base plates sit on. There's really nothing too interesting to talk about there. They were concrete columns. We used ram elements to get the interaction diagrams of the columns and verify that their capacity was adequate. Next was the piles and pile caps. As Paul mentioned earlier, the piles are 120-ton concrete filled 12.75-inch diameter steel pipe piles. That 120 tons is the compression capacity. They also have a capacity of 40 tons in tension. There were 4 of these large pile caps under the box columns, and depending on which one you're looking at, there was anywhere from 28 to 40 piles per pile cap. The pile caps are 6 foot thick, and they are designed for the capacity of the pile. So we knew if we ran through a load distribution to each of these piles, as long as the pile capacity was not exceeded, the pile cap was going to be adequate as well. So we have an in-house spreadsheet that we used to take the loads from the columns, apply those loads in the right locations, and figure out the load distribution to the piles. And we did determine that no pile was overstressed. So we did not need to do any reinforcing there. Next, we'll get into the construction phase a little bit. The general contractor was LF Driscoll, the steel fabricator and erector was Berlin Steel, and the scoreboard manufacturer was Daktronics. Of course, there were many other players involved in erecting and building this structure, but these were the 3 that we mainly dealt with as the structural engineers. So the schedule of construction in early 2022, some of the contractors were on board providing pre-construction services. By July of 22, we were already getting shop drawings to start reviewing some pieces. In August of 22, some of the contractors were able to do some early mobilization and get started. By October, that was the last scheduled regular season game. However, this was the year that the Phillies advanced all the way to the World Series, so the start of construction was delayed a little bit due to that. And it wasn't until about November 8th of 22 that full-scale demolition began. And then the end goal was to have everything open and operational by April 6th of 2023. The Phillies did ask to have the building turned over to them a little bit earlier than that so that they would have time to test the board, do training on the board, and all of the things that they needed to do to be able to really run with it on opening day. But April 6th was the end date when everything had to be working. As I mentioned, some of the contractors had pre-construction services. One of them was Daktronics, the video board manufacturer. When we were still in the design phase, they were providing us with guidance on deflection criteria of what their board could accommodate in terms of deflection. They were also giving us some sample connections of how that video board would attach back to the structure. Berlin Steel was involved early on, giving us guidance on availability of member sizes. With the tight construction schedule, we didn't want to end up in a place where we're speccing a member size that had a long lead time. So they gave us some guidance on what we should and shouldn't be specifying in terms of member sizes. They did also provide some feedback on the types of connections that they wanted to see, and there was a very strong preference for bolted connections just to eliminate the amount of field welding and really speed the schedule. Another piece that they had some input on was the construction sequencing of these of the cantilevers that overhang on the center field side. The boxes at each level is about 9 feet tall, and then the planned dimension of that cantilever is about 12 feet by 12 feet. We initially thought that that was going to be too big to ship and thought that all of this cantilever would have to be stick built in the field. So we had some ideas about how we thought that might be done, but when Berlin got involved, they said, no, you know what, we can ship these large boxes, and we'd really rather just hang 10 boxes. So that did have some impact on some of our connection designs and where the column splices happened, and we were able to react to that and accommodate their plans to speed construction. Now for steel submittals, we had 12 sequences of steel that we reviewed, and that was based on the installation timeline. We were reviewing these shop drawings between July and November of 22. We did have an open line of communication between Ewing Cole and Berlin Steel, so that when we would get these shop drawings in, we would do our initial review. We would often hop on the phone with them at the end of the review and say, hey, this is what we're seeing. Like, what were you thinking here? And they might explain something to us and like, oh, you know what, that makes sense. Maybe we need to rethink how we did that. Other times, maybe it was a misunderstanding or something, but through those phone calls, we were able to all get on the same page, adjust our comments accordingly, and then hopefully limit the number of reviews that the shop drawings needed to go through. So I think typically any reviews were limited to no more than 2 submissions. Early mobilization started in maybe August of 22. Some of the contractors were able to get in and do some surveying of existing conditions. They were able to install some protective measures up on the roof to protect the existing structure. And some select demolition was able to occur. And also they were able to install some small connection elements that wouldn't really be visible from the ground. Now, steel erection began immediately following demolition. The first box, I don't know the exact date, but that first box that you see going up and getting ready to be hung at the top of the structure went in sometime in early December of 22. Now, any job going into construction, there's always field issues that come up that nobody anticipated. So we had to react quickly to those because of the tight construction timeline. One of those issues you can see up on the screen circled in red, there were some bolts that nobody expected to be there. They were dummy bolts. They did not connect anything. Not really sure exactly why they were there. Our best guess is that it might have been a fabrication issue, that the columns came out and had some holes in them and they needed to plug the holes. So they just threw some bolts in. That's our best guess. But it was unfortunate because we needed to connect a beam in right at that location. But Berlin was able to get out, survey these bolt hole locations and sizes, and we were able to reuse a few of them and otherwise work around them by modifying our connection geometry to miss those bolts. That's just one example of one of those issues that came up that we had to try to react quickly and get some answers. Another challenge was for the catwalks, we had a mix of existing and new catwalks, and the intent was that the new catwalks would closely match the existing in terms of how far they project out from the columns. Scoreboard manufacturer, of course, wanted a uniform plane to make their attachments to. And when we were designing our new catwalks, we based those dimensions on the shop drawings that we had for the existing catwalks. But once the building was opened up and they were able to do some surveying of those existing catwalks, we found that they actually didn't stick out as far as we thought they did based on the shop drawings. So our new catwalks projected several inches beyond where the existing catwalks were. So Driscoll and Berlin surveyors were able to get out there and do a survey of all the different points on the catwalks. And we came up with a connection, a bracket connection that we could install on the face of the existing catwalks to extend that plane out a little bit, so that Daktronics would have a uniform plane to make their connections of the video board. Finally, there are some coordination things that had to take place during construction because we just didn't have the information during design. One of those things is a gap that exists between the video board and the catwalk. So at the top of the screen, you can see my little image there. The blue is the video board, and then Daktronics has these 3x3 HSS vertical members that run behind the video board to support it, and then those members are attached back to the catwalk. So just the way the framing is laid out, it results in a gap between the video board and the catwalk structure. So once the video board was in place, all of the adjustments were made. They were able to go out and survey these gaps and give us some dimensions, and we were able to come up with a detail to install some closure plates so that nobody could drop tools or get their foot stuck or anything like that in that gap. So now some final thoughts. Have some statistics that were provided by Berlin that I found to be pretty interesting. There were 1,126 field drilled bolt holes installed for this project. There were 11,700 field bolts installed. In terms of welding, there were 114 worker days of welding, 10,000 inches of fillet welds, 896 inches of PJP or CJP groove welds, and 1,460 inches of flare bevel welds. All of that work was completed by the end of January in 2023, and the board was indeed fully operational in time for opening day on April 6th of 2023. So I'd like to thank you for attending our presentation, and at this time we can entertain any questions.
Well, I will say that nothing came up in the Q&A that I can see. So obviously you did a great presentation.
Okay, well, thank you.
The question I would ask is, do we think that any of those bolt holes drilled in the field will help the Phillies win a pennant this year?
One can hope.
Truly. Well, once again, really appreciate you guys putting the presentation on. Very interesting. We did have one question just pop up. As the engineer record, were all the connections designed in-house, or were they delegated to the fabricator?
For the most part, for this job, we did design the connections in-house. I can't say with 100% confidence that we did every single one. We might have received a calculation here or there for a modification that the contractor wanted to make. But in general, the beam to column and the bracing connections, they were all designed by us in-house.
Guess we'll give another 10 seconds for people to formulate questions they may have. So how many times have you been able to go to the stadium and see the new scoreboard in person after the work was completed?
Honestly, me just one time. Unfortunately, I'm a mom of two very young children who can be difficult to take anywhere, so we don't get out too often.
I hear you.
No, it might have been twice by now. Once or twice.
That's good. It's more than zero, so that's
more than zero. Yes.
I'll take that as a win. We just got another question. What wind load was the sign designed for?
The sign or the video board?
Sign was in the question, but probably meant video board.
Okay. Could we go back to that slide? Oh, yep, there it is. So this is our wind loading diagram. We had a number of different zones that we looked at. The video board, we had 66 pounds per square foot on the video board. the Phillies sign, we had 38 over the gross area, 45 over the gross area of the light array, and 37 over the gross area of the truss tower. And I guess I should mention too, because this is ASCE 716, these are strength level loads. So they do seem high, but when you're comparing them back to what the structure was originally designed for, you could take these loads and multiply it by, a 0.6 to take them back to the service level loads.
Thank you. All right, excellent. I'm gonna say that's the questions we have for today. Once again, thanks for the presentation. I think we'll get the QR code posted in the Q&A area here for people to get their PDHs. There we go.
And there's also a link in the Q&A section with a link to the PDF as well.
So I want to thank everybody for attending once again. And certainly, being the time of year, happy holidays to all. And hopefully we'll see everybody again in January.
It looks like we did have one more question in the chat
Oh, did one pop up?
just now. Yeah.
That was Nicole thanking Paul Mary. And thank you.
No, right
Nikki.
below that, Ryan.
Oh, Ryan. Did you need to take advantage of increased pile capacities for short-term wind load? I'm not sure what the EQ is for. Was geotech involved in any of the reanalysis of the piles themselves?
I'm sorry, could you repeat the whole question again?
Did you need to take advantage of increased pile capacities for short-term wind loads? And he also said EQ. I'm not sure what that's for. And was geotech involved in any reanalysis of piles themselves?
Okay. No, we did not take advantage of any 1/3 increase for short-term loading. We didn't need to go that far. We did not have a geotech involved for this specific project since we didn't need to do any new foundations and we knew the capacity of the existing piles. And I think there was something about EQ for earthquake. I'm not sure what the question is about seismic. We did look at seismic loading on this, but it was so far from controlling the building. The wind loads were so much higher that seismic did not govern any portions of this design.
Thank you.
I have another question via email asking about the differential expansion in the board versus the truss structure.
That's an interesting question. There is a little bit of adjustability in the connections between the video board and the structure itself in terms of what the differential movement between the two is. I'm not really sure off the top of my head. But for the length of this video board, that did not wind up being a concern.
All right, I think that's all we got.
Yeah, definitely sounds like it. So everyone back to work. All right,
Thanks
everyone, have
again,
a good
Paul, Mayor.
holidays.
All right, thank you. Thanks for having us.
Thank you.
Yep.